Hello everyone, thank you for attending to this presentation. I will talk about my work at Météo France, which is supervised by Pierre Brousseau, Loïk, Berre, and Sylvie Malardel. And so, what we are currently wanting to do at Météo France is to build a strongly coupled data assimilation between the ocean and the atmosphere for our limited area model AROM. The strongly coupled part, meaning that we want the coupling to be performed in every step, including the minimization step, in opposition to a weak coupling, where the coupling does not occur, at least in the minimization steps. The reason why we are willing to do this is because currently AROM is running with an N-var scheme, in which the background covariances are estimated and not parameterized. So the cross covariances that are required for a strongly coupled data assimilation would be easier to estimate and not to parameterize. So this work is actually on the first steps toward this goal, with the estimation of the ocean atmosphere cross covariances that would be used in an inverse scheme. And we did that by building an ensemble of data assimilation with per-tube forecasts that are coupled to an ocean model. So I'm going to firstly develop a little the context, and then I will show you some results and finally investigate how they may vary or not. So first, the atmosphere model we used is the AROM model, so Météo France Limited Area Model, as I said before. It has 90 vertical levels, and it runs in several different configurations over different geographical domains. And the configurations can be deterministic runs, ensemble of prediction systems, or ensemble of data simulations. And the difference between these configurations can be, for instance, that over the metropolitan France, AROM runs with a 3D N-var scheme in a 1-hour data assimilation cycle, whereas on the overseas domain, AROM doesn't run without any assimilation, but it is coupled with an ocean mixed layer model in the forecast. So the ensemble of data assimilation we built in order to estimate all those covariances was over the Indian Ocean domain with a 2.5 horizontal resolution, 2.5 kilometers, sorry. It ran a 3D VAR scheme in a 3 hours cycle with perturbations applied to the observation, the lateral boundary condition, and to the model forecast through the use of ISPPT. And of course, it was coupled with the ocean model in the forecast. This ocean model is actually very simple. It's composed of independent vertical columns that don't go to the bottom of the ocean, as the aim is only to modelize the ocean mixing layer. The model only represents the turbulent submesh mixing and is only forced at the interface, at the surface, by the heat and momentum fluxes. So the model cannot represent the advection by the currents. And in this experiment, we did a relaxation towards another ocean model, more complex, more complete, from Mercator, which is called Psi4, every day at 0 UTC. And this relaxation was perturbed in the same way as the observations. So with this system, we didn't know beforehand if we would have any cross covariances at all. So we chose to study a situation with the most intense ocean atmosphere interaction we could figure, namely a tropical cyclone. The one we chose was called Batirai. It came pretty close to La Réunion Island, and at a very slow pace, which made that it spent several days in the range of La Réunion radars, providing us with many observations. On this figure, you have here in red, in the red rectangle, the limits of the Arome-Indian domain. You have in black what we call the best track, which is the trajectory of the cyclone as expertized afterwards by the forecasters. The plain gray plume is the ensemble of the trajectories of the cyclone as seen by every single member of our ensemble of data simulation. And the dotted gray plume is the same thing, but for an operational run of the Arome ensemble prediction system over this situation. So what we can see with this figure is that both spreads are quite comparable, meaning that the dispersion of our IDA is quite satisfactory, meaning that we can start investigating the results. So I will do this in 2 times. At first, I will start with some sigma b's that are the diagonal elements of the B matrix, and I will finish by the cross covariances. So here a general overview of what we can have with our experiment. You have on the left-hand panels the ensemble means for several fields, on the right-hand panel the sigma b's. So the top left panel is the ensemble mean for the atmospheric wind, and on this one we can see that we have a very clear structure for the cyclone, which means that our different members show the same structure, all of them. When we look at the sigma b's of the atmospheric wind, we can see that we have errors that are located around the eye wall, close to the wind maximum, and that here with the gray crosses, all the different members don't place the cyclone exactly at the same place. So we deduced that the background errors mostly come from these differences in location. When we look at the middle panel, which are the oceanic currents at the surface of the ocean model, we can see that we do have a longer memory of the ocean that is represented here with the higher speeds along the right hand of the trajectory, which is comparable to what is observed in the cyclone case. What we don't see here are the upwellings, which have to be missing because our ocean model cannot represent them. When we look now at the errors for this current, surface current, we can see that we also have a longer memory of the ocean in the errors, in the background errors, and that we have maxima that are associated with gradients and convergence and divergence areas. Finally, when we look at the oceanic surface salinity, a very volatile variable, we can still see the longer memory of the ocean with the lower values of salinity. Along the trajectory, we can see where the showers have diluted the salinity the most. And when we look at the sigma b's for the surface salinity, we can see here the volatile nature of this variable, since while the cyclone undoubtedly has an impact, the scattered showers that come afterwards have a greater impact on this field. So now that we have a horizontal point of view, it might be quite interesting to look at what happens on a vertical scale. So here you have a vertical cross-section with different variables. So on the top we have the meridional wind. We are here at 0 UTC, so the cyclone is not exactly on the vertical cross-section. So while we do see still pretty well the structure of the cyclone, we only see the side of the eye wall here. On the middle panel, we have the liquid water mixing ratio, on which we can also see the eye of the cyclone, and we can also see strong errors there, which actually coincide with the rain bands of the cyclone. So with background errors, we can make a physical observation of sorts. And when we look at the salinity here, so always the sigma b's, we can see that we have a strong patch of error after the behind the cyclone, and small to no errors right under or at the front of the cyclone. So if we look at what happens 12 hours later, we can see that the cyclone has moved westwards and come closer to the cross-section, because we can now see both sides of the eye wall on the meridional wind. We can see that the rain bands have also moved westwards. And we can see with the sigma b's of salinity that the errors that we had previously have slightly decreased, while new errors have appeared under the cyclone and been increased by the second wave of rain bands, meaning that the error actually propagates from the atmosphere into the ocean and remain there due to the longer memory of the ocean. So after this, we can finally start to look at the covariances, background covariances. So here you have all the several matrices of background covariances. All those small boxes are matrices of vertical covariances between two parameters, and they are all normalized by their respective absolute maxima. We have three boxes in this big matrix. So the first one is the atmospheric covariances, in which we can see patterns that we expected. We have then the second diagonal block, the oceanic covariances, and finally, what we will focus on, the cross covariances between the atmosphere and the ocean. So if we zoom in on one of the examples, we have here the cross covariance matrix between salinity and atmosphere temperature, with the depth of the ocean going down as we go down of the figure, and the height of the atmosphere going up as we go towards the right hand of the figure. What we can see on this example is that we do see the limits under which we don't have any more any significant covariances, and this limit is actually the thermocline, which separates the ocean mixed layer and the deep ocean mixed layer. And on this figure with on all the covariances with salinity, we can also see the surface mixed layer and its depth, as the salinity mostly evolves in the surface mixed layer. So, since we do have cross covariances, we can look at their variation. Do they vary at all? The first thing we looked at was the day-night cycle. So here you have the surface temperature of our ocean model during the night and during the daytime. And during the daytime, we do have higher errors on areas that have scattered showers and scattered clouds. So the background errors do vary with the day-night cycle. However, under the cyclone, we don't see any variation. So the cyclone seems to have an impact on the background variations. So let's look at that impact. With the cross covariances here between the ocean temperature and the zonal wind. So on the left, you have over the whole sea, and on the right, you have only under the tropical cyclone. And what we can see is that under the tropical cyclone, we have much more homogeneous signals, which reflects the increased turbulence under the cyclone. And we can also see that over the whole sea, the thermocline is about 30 meters deep, while under the cyclone, where the thermocline is 2 levels below, so about 50 meters deep, which is expected under the cyclone, but we wouldn't expect to be able to see this in the cross covariances and the background error cross covariances. Another final interesting result we found was that we can see how the surface mixed layer does fade in the ocean mixed layer, once more due to the increased turbulence under the cyclone. So to conclude, we built an ensemble of data assimilation with the ocean atmosphere coupling in the forecast steps, which we use to estimate the background error covariances during the Berre cyclone. From this, we found that most of the background error statistics can be interpreted physically, and that the cross-covariances vary with the underlying ocean atmosphere processes, meaning that we have a form of flow dependency, which is precisely what we want from an ENVAR scheme. So all this is very encouraging. So the next prospects are to do the same experiment, but over the the metropolitan France domain, with less intense atmosphere-ocean interaction. And this is undoubtedly a first step towards a strongly coupled ocean-atmosphere data assimilation in the AROM 3D ENVAR framework. So thank you for your attention, and do you have any question?
Thank you very much, Argan. That was great to see. So I'll go first to the Yopad for a question, if that's all right. So Hyung-Suk Kim would like to know a bit more about how you provide your ocean initial conditions in your experiments. Specifically, is the state geostrophically balanced? And could you say a bit about the ocean mixing scheme that's in use?
Okay, so the initial condition actually come right from the Mercator Psi4 model, which I mentioned, because we had to initialize it in a way. And the ocean mixing scheme that is employed is an eddy mixing scheme. And actually it was detailed in a paper from Cindy Brousseau in 2009, which I can send a reference in the Yopad if necessary.
I think that sounds perfect.
Okay.
So I'm going to ask a question, if that's all right. So ultimately, you want to try and use these covariances in your ENVAR scheme. So do you think you might have any issues with these cross covariances if you have a bimodal state under a tropical cyclone? So sort of thinking where there's two plausible cyclone tracks in half of your ensemble, or they sort of divert. Have you looked at any extreme cases like that?
No, we haven't done so yet, because for now we only estimated if we whether we would have any relevant cross covariances, and those tests would be, we thought they would be more relevant to do with an ENVAR scheme already implemented. So for now we don't have any answer.
Yeah. Okay. I'm not seeing any further questions on the Yopad, but if anything comes to anyone's mind, they can put them in there later. So thank you very much, Argan.
You're welcome.